Hello everyone, welcome back to this my YouTube channel, and here I'm going to be taking you guys through this Mohr circle problem for mechanics of materials. A point A on the structure in figure 3A is subjected to in-plane stresses as shown in figure 3B. They want us to use the stress element in figure 3B to draw the Mohr circle on the attached graph paper. Use the Mohr circle to calculate first the principal stresses in the xy plane, second the maximum in-plane shear stress, third the absolute maximum shear stress, and fourth the angle of rotation from the x-axis to the direction of the in-plane uh, principal stress 1, and fifth draw a stress element to show the in-plane principal stress is correctly oriented with respect to the x-axis. And part C is to determine the normal and shear stresses in the x prime, y prime directions and to draw a stress element to show the calculate stresses and mark the state of stress in the x prime, y prime directions on the Mohr circle. Note that the x prime axis is oriented at a 45-degree angle from the x-axis as shown in figure 3A. So first we have to calculate the principal stresses. And this is simple enough because as we are familiar with the Mohr circle, the first thing we have to do, since principal stress 1 is equal to um, sigma average plus R, and sigma P2 is equal to uh, sigma average minus R, is we have to calculate this value of sigma average. So sigma average is equal to sigma x plus sigma y over 2. And if you look at this Mohr circle on the bottom here, we can see that our sigma y is given by 40 megapascals and our sigma x is given by 120 megapascals. And both of these are positive since they are in tension, as you see over here. And thus our sigma average will be equal to um 120 plus 40 over 2 megapascals, which is in turn equal to 120 plus 40 is equal to 160, and 160 over 2 is equal to 80. So 80 megapascals. Now we have to calculate our R value. So basically, R is given by this equation over here is basically the square root of sigma x minus sigma y over 2 squared plus tau xy squared. And over here, note that we have a shear stress of 30 megapascals, and it's positive because over here the shear force is up, but it doesn't really matter because the shear force is squared anyways. So our R value will be equal to square root of 120 minus 40 over 2 squared plus 30 squared. And this is equal to the square root of 120 minus 40 is 80. So 80 over 2 is 40. And 40 squared is 160. So 160 plus 900, because 30 squared is 900. And this is equal to uh 1060, square root of 1060, which is equal to Um, actually, I just discovered that I did this part wrong. So 120 minus 40 is not equal to 160. I accidentally added them. It's actually equal to 80. Or yeah, it's equal to 80. Um, so yeah, 80 and then 80 divided by 2 squared is equal to 1,600. And 1,600 plus 900 to 2,500. So we have square root of 2,500 here, which is equal to 50. All right, so now we have our sigma average and our R value. So now we can calculate that principal stress 1 is equal to 80, and this is megapascals as well, plus 50, equals 130 megapascals. And that sigma P2 is equal to 80 minus 50 equals 30 megapascals. This will give us the information needed to first graph our Mohr circle. So here I have condensed everything down. And to graph our Mohr circle, remember that our principal stress values, so our principal stress value of 1 will be over here, which is uh which is 130. And our principal stress value of 2 will be equal over here. And then the sigma average will be at 80 megapascals. And the radius, note that the radius over here is equal to 50 megapascals. Um, and to graph the radius, we can kind of map over here the 50 and the -50. And if we connect these points, we will get our Mohr circle. So here's our Mohr circle graphed. And now our goal is to find the maximum in-plane shear stress. That is part 2. Because we have not found the principal stresses in the XY plane. So that's the next step we're going to do. So the next step they ask us is to find the maximum in-plane shear stress as we saw. So the max in-plane shear stress is always just our R value. So we can say that uh, T max in plane. So so T max in plane is equal to R is equal to 50 megapascals. And let's take a moment here to see where we are actually getting all of these equations that we just used. Um, so it's basically just from our transformation of stress equations where we have Tmax in plane equation over here. And notice that it's always equal to R. So these two values here are always the same. So what about part 3, finding the absolute maximum shear stress? Well, this is coming from our out of plane Mohr circle, because we have to remember that this is a 2D problem over here. And thus there are only two stresses, two principal stresses, or as we usually call it, sigma 1 and sigma 2. But we also have to take into account sigma 3 because sometimes there are three-dimensional problems and there's always a z-axis over here pointing outwards. So you have to take into account the z-axis. That's why it's called our out-of-plane Mohr circle because it is out of the plane. And we have to always remember that sigma 1, by convention, And that's just the definition of sigma 1. Sigma 1 is always the greatest, followed by sigma 2, followed by sigma 3, which is the smallest. Now, when we are looking at a two-dimensional problem, we will have these values, sigma 1, sigma 2, and sigma 3. However, sigma 3 in a 2D problem is always equal to 0. Um, and our goal is thus to compare these uh, the sigma 3 with our principal stress 1 and principal stress 2 values to determine which one is our sigma 1 and sigma 2 values. Because principal stress 1 is not necessarily sigma 1, and principal stress 2 is not necessarily sigma 2. Principal stress 2 is not necessarily sigma 2. So as we see from our found values for principal stress 1 and principal stress 2, over here it so happens that our our sigma 1 lies uh over over here actually. Well, sigma 1 is always the greatest. So our principal stress 1 will be equal to sigma 1, and our principal stress 2 will be equal to our sigma 2, since sigma 2 is less than sigma 1, and our smallest value over here is sigma 3, since sigma 3 is 0 in a two-dimensional problem. So we can draw our outer plane Mohr circle as such. So here we have placed our outer plane Mohr circle, which is this one over here. And note that since sigma 3 is equal to 0, sigma 3 is found here. So our absolute maximum shear stress is always going to be equal to T max absolute is always going to be equal to the maximum stress minus the minimum stress over 2. And since sigma 1 is the maximum stress and sigma 3 is minimum stress by definition, we will use those values. So sigma 1 is equal to our principal stress 1 here in this specific problem, so equal to 130. And sigma 3 is equal to 0. We divide this by 2 to get 65 megapascals. So our Tmax absolute value is found from this equation. Uh, it's found from this equation over here, which is the Tmax absolute equals sigma 1 minus sigma 3 over 2 over here. Okay, so now we have found the absolute maximum shear stress. And we will want to find the angle of rotation from the x-axis to the direction of the in-plane principal stress, sigma p1. So the first thing is to plot our x and y on the in-plane Mohr circle, which is the inner circle in this diagram here. And I'm going to first move some things around first. So looking at our um, xy stress element over here, we see that we have a sigma y of 40 megapascals and a sigma x of 120 megapascals. So we want to graph the locations of these two values on our Mohr circle here. And basically sigma x will be at 120, so 120 is over here. And then we have a shear force of 30 megapascals, which on our Mohr circle diagram, the positive 30 megapascals is going downwards by the convention over here. Um, and thus we will drop down by 30. So 30 is about here. 30 is about right around here. So we will do at this location of the Mohr circle. It will be the x value. And then now we can find our y value similarly, or we don't really have to do the whole calculation again, but y is going to lie at 40 and 30 for the shear force because the value for sigma y is 40 megapascals, and we again have a shear force of 30 megapascals, which also happens to be positive. So we can connect our two x and y. This is y. See if we can draw a straight line. Okay, perfect. So we have graphed our location on the Mohr circle. And on the Mohr circle, what is necessary to remember is that this angle here is actually equal to 2 theta p1. And this makes sense if you think about it logically because y and x, the distance between y and x is actually 180 degrees. But on the stress element is only 90 degrees. So we see that all the angles are multiplied by 2 in our Mohr circle, um, relative to in real life. So this angle over here is going to be 2 theta principal stress of 1. And I believe this one is going to be 2 theta principal stress of 2. But over here, we only need to find the theta principal stress of 1. So to do this, we can use our trig identities of tan or sine. If we use tangent, we will have to use opposite over adjacent, which is the shear force over the sigma x. If we use our sine value, we can simply use our opposite over hypotenuse, which is going to be our shear value over the r value. So let's use sine. So that means that the arc sine of the shear force, which is 30, over sigma x, which is 120, will be equal to 2 theta principal stress of 1. And plugging this into a calculator, we will find that principal stress of 1 is equal to um, oh yeah, actually I'm sorry about something. So sine is actually opposite over hypotenuse. So as I mentioned earlier, we should have used our R value, which is equal to 50 megapascals. So uh, in the denominator will be 50. So inverse sine of 30 over 50 is equal to um, some value. And then we will divide that by 2 to get that theta principal stress of 1 is equal to 18.4 degrees. And remember to change your calculator to degrees if it's in radians naturally. So you might be wondering why people chose the negative, well, the axis pointing down to be positive for the shear force. And That is because actually there's a pretty good reason for it. It's because it's in the same direction as the angle we would use to rotate our stress element in real life. So, as you can see, the counterclockwise convention is positive. So, this means that this angle is actually going this way. So, in real life, a rotation counterclockwise by 2 theta p1 on the Mohr circle will correspond to a rotation counterclockwise of the stress element by 18.4 degrees. So we can solve our problem 5 now. So we first draw our stress element as we have over here, or we can just directly show it on this stress element because originally the x-axis is pointing this way. So what we want to do is to, let me see if I can actually move this down a bit. Okay, okay, perfect. So we have our x-axis and rotating it by 18 degrees would give us the stress element somewhere over here, which is like going to look something like this. Um, where this one is our original um x graph, and this is wait, oops. This is our y, and these are just we just got these from this diagram. So the x is parallel to the x in the figure 3b, and the y also. Um, and we rotated it counterclockwise by 18.4 degrees to get our principal stress one located here. All right, so now part 5 is completed. Uh, or not fully completed yet because we have to show that sigma p1 is in tension and that the 30 megapascals is also, and also our principal stress 2 is going to be pointed this way. And remember that our principal stress 1 is equal to 130 and our principal stress 2 is equal to 30. So that's what we will put. So for part C, we are asked to find the normal and shear stresses in the x prime, y prime direction and draw the stress element to show the calculated stresses. So for this problem, it's kind of the reverse of what we just did in part 5 of part B. And first you have to note that we're twisting the XY stress element as we see over here. And we're going clockwise by 45 degrees to end up at y prime, x prime. And remember that everything in our Mohr circle, all the angles are doubled. So we will have to multiply 45 degrees by 2 in order to get the angle we will have to rotate clockwise in our Mohr circle. So 45 degrees times 2 is equal to simply 90 degrees. So this means we will have to rotate our x and y by 90 degrees clockwise on a Mohr circle to end up um, at our x prime and y prime directions. So x prime will be over here and y prime will be over here. And now, draw the source element to sort of calculate the stresses. So we want to find the normal and shear stresses in the x prime y prime direction. So I'm going to use a different color now to distinguish between the parts we've already done. Um, so our shear stress is given by the y coordinate. So if we draw a line up from x prime, we will get the location of the normal stress as the x-axis and the location of the shear stress as our y-axis. So again, we can calculate these two values by first finding this angle over here, which we will call um, theta prime. Or rather, I don't know if any of you catch that, but it's supposed to be 2 theta prime, since theta prime is the angle we will have to rotate our stress element in order to end up at x prime. So 2 theta prime is equal to that angle. So how do we find that angle? So 2 theta prime is equal to, what is this angle? This angle is 2 theta principal stress of 1. So principal stress of 1 is 18.4. So 2 times 18.4 degrees. Um, and this angle is 90 degrees. So plus 90 degrees. And then all that um subtracted from 180 degrees because 180 degrees is the angle of this whole section. It's simply a straight line. So we'll calculate that as 53.2 degrees. And thus theta prime will be equal to 52 degrees divided by 2, which is 26.6 degrees. Um, okay, so now we can use this angle in order to determine our shear stress and normal stress. So first our shear stress, which is tau prime, is going to be equal to um well sine of tau prime over r is going to give you, or rather arcsine of tau prime over r, so opposite over hypotenuse, is going to give you this angle 2 theta prime. So this means that um, sine of 2 theta prime, which is sine of 53.2 degrees, is going to give you tau prime over r, which is 50. So tau prime will be equal to 40.04 megapascals in the positive direction because it's pointing downwards in the positive direction according to our Mohr circle over here. Um, so it's necessary to note that the tau is actually tau xy in the on the x phase in the y direction. And this subscript will be important if you are doing this on an exam. So always specify the specific direction of tau. Okay, so our second step is to find our sigma, which is the normal stress. So for the sigma x prime, we have to do some additional calculation. First, we have to note that um so our cosine of 2 theta prime is going to give us um this distance over here, but it's not going to give us the location on the x-axis, or rather on the sigma axis. So what we have to do is we have to equate it to sigma average minus um minus our cosine to theta prime is equal to sigma x prime. And this is because sigma average is this whole distance over here, and our cosine to theta prime is this distance over here. So in order to find the location of this x coordinate, we have to do sigma average minus r cosine to theta prime. So we basically have sigma x prime is equal to sigma average, which is equal to um okay, we have to scroll up. 80 megapascals. 80 minus r, which is 50, cosine 50 3.2, and this is in turn equal to 50.05 megapascals. And now it's time to draw a graph of our stress element. So we're rotating the actual element by 45 degrees so that the element ends up being very straight. So the element will be oriented straight, and we're going to draw the element over here. So and the sigma x prime is going to be uh positive because it's right of the zero. So it's going to be in tension sigma x prime, and our shear stress is going to be positive as well. And we use the tail-to-tail and head-to-head method. So this is our shear xy prime. Now we did forget to do one step, and that is to calculate sigma y prime. So sigma y prime is going to be the location over here. This distance over here, or rather from the x-axis, the distance it takes to get here. So we can calculate that as again, wait, what are we? It will be sigma average plus r cosine 2 pi, 2 theta prime, which is equal to 80 plus 50 cosine 53.2 degrees, which is equal to 110 megapascals. And thus this will be our sigma prime, and again it will be positive because it lies to the right of the zero. Um, the zero is here, so it'll be in tension as well. So sigma y prime, and our values are given by these. So 110 megapascals, 50.05 megapascals, and 40.04 megapascals. So we have thus solved this whole problem, and I hope this video was helpful to you all. See you in the next video. Bye.